Hi, my name is Hannah Lyons, and I will be discussing electrons and atoms, which is Chapter 5 in the textbook. This chapter covers the Bohr model, quantum mechanical model, atomic orbitals, electron configuration, Aufbau Principle, Pauli Exclusion Principle, and Hahn's rule. This video is going to cover and explain all of these topics. Niels Bohr was a young physicist and student of Rutherford who developed a new atomic model. He changed Rutherford's model to incorporate newer discoveries about how the energy of an atom changes when the atom absorbs or emits light. He considered the simplest atom, hydrogen, which has one electron. Bohr proposed that an electron is found only in specific circular paths or orbitals around the nucleus. Each possible electron orbital in Bohr's model has a fixed energy. The fixed energies an electron can have are called energy levels. The electrons of an atom cannot exist between energy levels. To move from one energy level to another, an electron must gain or lose just the right amount of energy. A quantum of energy is the amount of energy required to move an electron from one energy level to another energy level. The energy of an electron is therefore said to be quantized. The Rutherford model and the Bohr model of the atom describe the path of a moving electron as you would describe the path of a large moving object. Later, theoretical calculations and experimental results were inconsistent with describing electron motion this way. In 1926, the Austrian physicist Erwin Schrödinger used these calculations and results to devise and solve a mathematical equation describing the behavior of the electron in a hydrogen atom. The modern description of the electrons in atoms, the quantum mechanical model, came from the mathematical solutions to the Schrödinger equation. Like the Bohr model, the quantum mechanical model of the atom restricts the energy of electrons to certain values. Unlike the Bohr model, however, the quantum mechanical model does not specify an exact path the electron takes around the nucleus. The quantum mechanical model determines the allowed energies that an electron can have and how likely it is to find the electron in various locations around the nucleus of an atom. Solutions to the Schrödinger equation give the energies or energy levels an electron can have. For each energy level, the Schrödinger equation also leads to a mathematical expression called an atomic orbital. An atomic orbital describes the probability of finding an electron at various locations around the nucleus. An atomic orbital is represented pictorially as a region of space in which there is a high probability of finding an electron. The energy levels of electrons in the quantum mechanical model are labeled by principal quantum numbers, n. These numbers are assigned the values n equals 1, 2, 3, and so forth. For each principal energy level greater than 1, there are several orbitals with different shapes and at different energy levels. These energy levels within a principal energy level constitute energy sublevels. Each energy sublevel corresponds to one or more orbitals of different shapes. The orbitals describe where an electron is likely to be found. Different atomic orbitals are denoted by letters. As shown in this figure, s orbitals are spherical and p orbitals are dumbbell-shaped. The probability of finding an electron at a given distance from the nucleus in an s orbital does not depend on direction because of its spherical shape. The three kinds of p orbitals have different orientation in space. This figure shows the shapes of d orbitals. 4 of the 5 kinds of d orbitals have cloverleaf shapes. The shapes of f orbitals are more complicated than the shapes of d orbitals. As shown in this table, the number and types of atomic orbitals depend on the principal energy level. The lowest principal energy level, n equals 1, has only one sublevel called 1s. The second principal energy level, n equals 2, has two sublevels, 2s and 2p. The 2p sublevel is of higher energy than the 2s sublevel and consists of 3 p orbitals of equal energy. The second principal energy level has 4 orbitals. The third principal energy level, n equals 3, has 3 sublevels. These are called 3s, 3p, and 3d. The 3d sublevel consists of 5d orbitals of equal energy, making the third principal energy level have 9 orbitals. The fourth principal energy level, n equals 4, has 4 sublevels called 4s, 4p, 4d, and 4f. The 4f sublevel consists of 7 f orbitals of equal energy. The fourth principal energy level has 16 orbitals. As shown in the table, the principal quantum number always equals the number of sublevels within that principal energy level. The number of orbitals in a principal energy level is equal to n squared. Therefore, the maximum number of electrons that can occupy a principal energy level is given by the formula 2n squared. The 3 rules for writing the electron configurations of elements are the Aufbau Principle, the Pauli Exclusion Principle, and Hahn's Rule. These 3 rules tell you how to find the electron configurations of atoms. Let's start with the Aufbau Principle. According to this principle, electrons occupy the orbitals of lowest energy first. The orbitals for any sublevel of a principal energy level are always of equal energy. Next is the Pauli Exclusion Principle. According to this principle, an atomic orbital may describe at most 2 electrons. For example, either 1 or 2 electrons can occupy an s orbital or a p orbital. To occupy the same orbital, 2 electrons must have opposite spins. Spin is a quantum mechanical property of electrons and may be thought of as clockwise or counterclockwise. And finally, we have Hahn's Rule. According to this rule, electrons occupy orbitals of the same energy in a way that makes the number of electrons with the same spin direction as large as possible. Electrons then occupy each orbital so that their spins are paired with the first electron in the orbital. Next is an example chart that will show us the electron configurations of selected elements. So looking at this diagram, let's talk about oxygen. The oxygen atom contains 8 electrons. The orbital of lowest energy, 1s, has 1 electron, then a second electron of opposite spin. You can see that here. The next orbital to fill is 2s. It also has 1 electron, then a second electron of opposite spin. One electron then occupies each of the 3 2p orbitals of equal energy. The remaining electron now pairs with an electron occupying one of the 2p orbitals. The other 2p orbitals remain only half filled with 1 electron each. Therefore, we get the electron configuration 1s2, 2s2, and 2p4. And all of those numbers add up to 8, and we have 8 electrons in the oxygen atom. This is the end of this video, and I hope you find it very helpful and have now learned a lot more about electrons and atoms.